Good evening. So today we are going to go through more examples on shearing stress for thin wall analysis, and I've put this example on Avenue to Learn. Okay, so let's look at example number 1. So this is the first one that we want to do. Okay. So knowing that a given vertical shear V cause a maximum shear of 50 megapascal in a thin wall member, having the cross section as shown, determine the corresponding shearing stress at point A, at point B, and then at point C. So we are given that tau max is equal to BQ, or for this case, I'm going to draw my transformation. Y and Z, rotation X, and we're going to have Vy over IZZ QZ over T. Okay. And we given that the maximum shear is 50 megapascal. So what we realize for this structure over here, it has a constant thickness. Okay, constant thickness of 10 millimeters. Okay, or 0.01 meters. So we know that maximum shear will be at the centroid. So we are aware, right? Again, one of those problems that they did not ask us to find the stress. Okay, so we know that our maximum stress will occur at the centroid. Okay, so this is at the centroid. Why at the centroid? Because the thickness is sorry, I do apologize. It's not constant thickness. I do apologize. Because you have 10 millimeters over here, you have 12 millimeters on the vertical web. So I do apologize. It's not constant thickness. So we don't know where it is. Okay, I will correct my statement. We don't know where it is. So we have to now identify the first moment of area at point A, first moment of area at point B, and first moment of area at point C. And the formula that we're going to use is tau max equal to By over IZZ QZ over T. So we have to find the QZ over T ratio. Okay, so the maximum shear stress location is dependent on the QZ over T ratio for thin wall. Yeah, ratio for thin wall. Okay, so now we know that. So we're going to design the shear flow, as we already know that the web, major web, control the shear flow. Okay, so this is our major web. And I tend to do this, okay, and it does not really matter whether you do inwards or outwards, okay? So what I like to do is when it's above the centroid, okay, and then when it's below the centroid, usually above the centroid, our point, the shear flow flowing into the what? Into the major web. Below the centroid, I make them flow away from the major web, okay? But the most important thing, we have identified our terminus. Okay, the most important thing, as I said, we have identified our terminus. So this is our T1, this is our T2, this is our T3, and then this is our T4, and then this is our T5. Okay. So a rule that I'm going to write down here, okay, that you can apply for thin wall analysis. So this is which rule now? I can't remember how many rules I've written down already. Okay, I just going to put it as a rule down here. Okay. So for thin wall analysis, the analysis starts from the terminal. Okay, it starts from the terminal. Okay, so if we were to look at A, all right, we know this structure over here is more or less a white flange. Okay, we know it's a white flange. Oh, sorry, at point A. At point A is a white flange. Analysis. Okay, is a white flange. Analysis. Okay, so if we just focus on point A, right, and I'm going to sketch the Q, the shear flow Q, right? So this is our T1. When it reach A, this is the area that you have to consider. Okay, from the terminal. Remember, the analysis starts from the terminal. Okay. So when this is the case, we can find the Q Z at point A. Okay. So we are aware I'm sketching the centroid. So this is my centroid or our centroid. And also our ZZ line. Okay. So QZ at A. So when there's Z of interest, this is usually my width. This is usually my depth. Okay. So the width is 12. The depth is 30. And then we have to make up for the Y bar. So this is the width, depth. The Y bar will be equal to 25 plus 10, right? 25 plus 10 plus by 30 divided by 2. Okay. So this will be equal to 25 plus 10 plus by 30 divided by 2 times by 30 times by 12 is equal to 18 times 10 to the power 3 millimeter cube, or 18 times 10 to the power 6 meter cube. Okay, so that's a QZ at point A. So when we do QZ at point A, what we realize that we can find the shear at point A is equal to Vz or Vy over Izz, Qz, and then divide by a thickness of 12 times 10 to the power minus 3. Okay, so 18 power minus 6 divided by 12 power minus 3 is equal to 1.5 times 10 to the power minus 3 Vy over Izz. Okay. Then the next one we're going to find at point B. So point B, as you can see, is just before the vertical web, right? It's along the horizontal flange and before the vertical web. So we know that this is the terminal. So I label this terminal, I can't remember, terminal 2, right? This is terminal 2. The area of interest now, right? You know the flows do this, right? The area of interest, let me use a different color. Now the area of interest changes. Okay, the area of interest now is this now for point B. Okay, so again, point B, I usually put Q over here. So point B is also a wide flange analysis. And we just use Q. And then QZ at point B will be, so now the width is equal to what? The width is 40. The depth is 10, right? And then the Y bar is 25 plus by 10 divided by 2. Okay. So this is 25 plus 10 divided by 2. Times by 10 times by 40 is equal to 12 times 10 to the power 3 millimeter cube, or 12 times 10 to the power minus 6 meter cube. Okay. So again, we can find our shear stress at point B will be equal to Vy over Izz, right? Qz divided by, now the thickness change, right? The thickness now is 10 millimeters. Okay. So 12 power minus 6 divided by 10 power minus 3 is equal to 1.2 times 10 to the power minus 3 Vy over Izz. Okay. So the next thing we're going to do is we're going to look at point C now. Okay, so point C is also a wide flange analysis. Usually you can see for wide flange analysis, the shear flow comes from 3 separate or more than one separate or more than one terminal. If it's box beam, it's usually one terminal only. Okay. So this is our Q. Then from here, I'm going to take just so QZ at point C. I'm going to use the QZ at A, okay, which is 18 times 10 to the power 3 plus the width now, right? So point C, I do apologize. Point C is now over here. This is our point C. So now we are going to take the area. This area we're going to take. Okay, we're going to cover ourselves this area. Okay. And then now the width, so is 80, 92. The depth is 10. The Y bar is equal to 25 plus by 10 divided by 2. Okay. So this is 18 times 10 to the power 3 plus which is 27.6 times 10 to the power 3. So 18 power 3 plus 27.6 power 3 is equal to 45.6 times 10 to the power 3 millimeter cube, or 45.6 times 10 to the power minus 6 meter cube. Okay. So the shear stress at point C will be equal to Vy over Izz, right? 45.6 times 10 to the power minus 6. And then now the thickness, you're going to take the smallest thickness over here, right? So this is the thickness now is in fact 12 millimeters, not 10 millimeters or 92, okay? So it is 12 millimeters. So this is equal to 45.6 power minus 6 divided by 12 power minus 3. So it's 3.8 times 10 to the power minus 3 Vy over Izz. So from here, after knowing that point B, which has the smaller thickness, did not generate the highest Q over T ratio, right? That confirms that at the centroid, okay, so because there's point C down here, I'm going to call this point alpha, is where maximum shear will occur, because the thickness is 12 millimeters, and at point C is 3.8 times 10 to the power minus 3 already, okay, which is greater than at point B, which 12 times 10, 1.2 times 10 to the power minus 3. No doubt it has the lower thickness, right? You can see the thickness is different at point B and point C. So now we're going to find the shear stress, no, not shear stress, the Q Z at point alpha now. Okay, so this will be equal to 45.6